Okay, hi everyone. So in this screencast, I'm going to be talking about higher order derivatives, so second derivatives and third derivatives and so on and so forth, with particular emphasis on the second derivative, okay? Why the particular emphasis on the second derivative? Well, graphically, the second derivative is particularly helpful in looking at a particular graphical feature called concavity, which I'll get to in a minute. You don't have to know what that word is quite yet, all right? Beyond the second derivative, when you get to the third derivative, fourth derivative, etc., graphically, those significances tend to just become very clumsy and hard to imagine. We can still algebraically take successive derivatives, but their significance tends to be less and less important because it just becomes sloppy to think about graphically. What I've drawn right here is the red function, f of x, and sure, you can go ahead and imagine this is a quadratic, it's a parabola, okay? And I wrote here, at x equals x naught, f prime of x is positive, or I could have written this statement here succinctly by saying f prime of x naught is positive, all right? I also want to bring your attention to the fact that if we look at x values that fall on this part of the parabola, and yes, I could extend back here, I'm going to go there in a minute, all right? If I look at this, like any x values in this part of the parabola, remember we talked about how a function can be increasing, and a function can be increasingly increasing or decreasingly increasing. And if I look at this here, if I look at kind of the slopes of the line's tangent at various values of x, I notice that at x equals x naught, at that moment in time, x naught for example, f prime is positive, but also the rate of increase is increasing. In other words, the slopes of the line's tangent are positive, right? But the slopes of the line's tangent are getting more positive. So if I look at that, that tells me this. Okay? I'm going to write something down here that is incredibly important, and I'm going to talk about it a great deal. We know f prime of x describes f of x as increasing or decreasing. Okay? Therefore, f double prime of x describes f prime of x as increasing or decreasing. Let's focus on this statement for a minute. The first one, I think we have spent a lot of time talking about it. Let's talk about this second one. When we say f double prime describes f prime as increasing or decreasing, well, since we know f prime of x describes the slope of the tangent line, right? F double then describes whether the slope of the tangent line is increasing or decreasing. So once again, f prime of x describes whether the function is increasing or decreasing. F double prime of x describes whether the slope of the tangent line is increasing or decreasing. And if you look over here, at that moment at x naught, you can see that at x naught, not only is the function increasing, but the slope of the tangent line is also increasing, right? Because at that moment at x naught, the slope of the line tangent is positive, but then it becomes more positive. So what you notice here is sometimes you'll see this. I've actually seen this only once, like the 0th deriv of f, which is a very odd thing to say. But this is the first derivative of f of x. This is the second derivative of f of x. So the 0th deriv, so to speak, is sometimes referred to as f of x. As we go up in the order of the derivative, right, the nth order of the derivative describes how the n minus 1th order of the derivative is increasing or decreasing. All right? So how about this function? Let's take a look at this one. How about at this point? Let's call this at the point, I'll just make it up, let's call this negative 2. Question for you. Is f of negative 2 positive or negative? Is f prime of negative 2 positive or negative? And is f double of negative 2 positive or negative? Go ahead and put in the inequalities and then replay me for the answer. Well, it's very clear that that's the case, right? The slope of the line tangent is negative, hence this point here, and f of negative 2 is obviously above the x-axis. How about f double at negative 2? Well, let's see. What's happening to the tangent lines what is happening to the slopes of the tangent line? Let's see. Very negative. Oh, interesting. At negative 2, the slopes of the line's tangent are increasing. Look, very negative, less negative, less negative, 0, positive, more positive, more positive. So at negative 2, the slope of the line tangent is increasing. So here's an interesting thought. It is possible for there to be a point where the first and second derivatives, right, have opposite signs, because a function can be decreasing, yet the slopes of the line's tangent could be increasing, right? Really interesting, okay? Just some semantics. When you say this, you say f double prime of x, okay? Or if you are in a particularly cool group, f double of x, okay? F double of x, f double prime of x, you dropping the prime word, everyone knows what it means if you're in the right group of people, okay? If you're not in the right group of people, then frankly, I would leave the party. All right, what about the Leibniz notation? Well, f double prime of x, just like we know that f prime of x could be written as dy by dx, f double prime of x is d squared y by dx squared. How do you say this? You say this d squared y by dx squared. And I know someone, maybe it'd be you, Arjun, if you weren't playing me on 8 times speed. Someone's wondering, Miss Yam, why is the 2 in a different place? Why isn't the squared like, why is it the same? Why is it in a different place? I'll tell you why. Because when you say f double prime of x, this is the same thing as, now watch this, ready? This is the same thing as take the derivative with respect to x of dy by dx, right? This is saying the same thing as take the derivative with respect to x of f prime of x. I mean, that is actually what the second derivative is. It's taking the derivative of the first derivative. And if you look here, by just reading across, d dy, that becomes d squared y, dx dx, this is dx squared. Someone once asked me, then why shouldn't there be like a parenthesis around the dx squared? And the answer is yes, you would think there would be. And I think the reason why there's not is because that just looks stupid. It looks ridiculous. And yes, I think it looks it looks ridiculous, but I've got to clean it back up. D squared y by dx squared. All right? Now let's just practice taking the second derivative. And you're going to notice a couple of things here. You ready? All right, let's let f of x equals 6x cubed plus 4x squared minus 11. All right, everyone, go ahead and take the first derivative. F prime of x equals what? Very good. 18x squared plus 8x. Oh no, what is the derivative with respect to x of negative 11? It is 0. Let's take the second derivative. F double prime of x is going to equal 36x plus 8. Okay? Now, once we have, the mechanics of taking higher derivatives, you can imagine here that it just becomes a matter of proceeding. After triple prime, it starts to look a little silly. After triple prime, if you're asked for the fourth derivative, what you'll normally see is this. Rather than writing 4 prime symbols, you'll see the fourth derivative of f. Now here, the fourth derivative of f is equal to 0. Now what's interesting is, once your derivative, the order of your derivative, right? If you take successive derivatives, once you hit 0, guess what happens, everyone? Every successive derivative is naturally going to be 0. You understand? Okay. How about this? Let's do this. Ooh, I have an idea. Okay, let f of x be described by this function. Let's go ahead and why don't you all just sketch sine x from negative pi to pi, okay? Oh, for heaven's sake. Miss Yam, what's wrong with me? End of the day, boys and girls. End of the day. All right. Okay, let f of x equals sine x. And I'm only looking at this function from negative pi to positive pi. So let f of x equals sine x. Now, I cannot ask you to analytically find f prime of x. Tell me why, everyone. Because you'd say, Miss Yam, we only have the power rule and the product rule. We only know how to take derivatives of things where x is raised to some rational exponent. This is not a power function. This is not x raised to some exponent. This is a trigonometric function. And Miss Yam, we have not learned how to take the deriv of a trigonometric function. And I would say, good job. All right, I would like to do this. Ready? This is pi over 2, of course. So pi over 4 would be right here. 0, obviously, and then we know this is negative pi over 2. And this is negative 3 pi over 4. Okay, now I have these questions for you. Okay, an inequality symbol is going to go in each of these. A and B give you two quantities to compare. Which one is greater? You can go ahead and try it on your own and then replay me for the answers. All right, I'm going to start going over the answers now. Well, let's take a look at f prime of pi over 2. F prime of pi over 2, if I look at the function at pi over 2, I see that that's a point of horizontal tangency. So f prime of pi over 2 equals 0, making a note to myself. F double of pi over 2, we're talking about the whether or not the slopes of the line's tangent are increasing or decreasing. Let's just take a look at, slopes of the line's tangent here. Oh, at pi over 2, the slopes of the tangent lines are decreasing. So I know f double at pi over 2 is negative. So which is greater? F prime of pi over 2. Nicely done. Second one, f prime of pi over 4. Well, this is positive. Why? Let's go upstairs and take a look. F prime of pi over 4 is positive. What is f double of pi over 4 doing? Slope of the line tangent is positive. F double at pi over 4 is negative. So which one's bigger? This one. Okay, very good. All right, some more questions on this same graph. Okay. All right, two more questions. Again, a comparison. Which one is bigger, f of negative 3 pi over 4 or f double of negative 3 pi over 4? Well, let's see. F of negative 3 pi over 4 is right here. That is a negative value. F double of negative 3 pi over 4, let's take a look at how the tangent lines are behaving at negative 3 pi over 4. Tangent line is negative. Oh, less negative. Oh, less. F double at negative 3 pi over 4 is positive because the slopes of the tangent lines are increasing. Do you see that? This way. D is a thinking question. Is there a point at which you think f double equals 0? Think about this. Is there a point at which you think f double equals 0? And tell me why. Pause me now and then replay me for the answer. Okay, if I look at this, I'm going to take a look at this function here. And if I look at the tangent lines, and maybe you are one who still likes to sketch little tangent line segments, okay? Something interesting happens here. It seems like the slopes of the tangent lines, very negative, less negative, 0, slightly positive, more positive, more positive, less positive, less positive, less, interesting. So it seems like f double is positive, right, for these values of x. So it seems like, if I were to eyeball this, the tangent line slopes increase, and then they start to decrease. And I think we called this, before we had any of this calculus vocabulary, we called this a wacha. it wasn't we, maybe it was just Daniel. But the point is that f double is positive, then it's negative. And when we say f double is positive, what we're saying is the slopes of the tangent lines increase. And at some point around here, the slopes of the tangent lines start to decrease. That means f double is positive, then at some point around here, it becomes negative. So it appears that at x equals 0, comma, f double equals 0, because at x equals to 0, comma, f double of x switches from being positive to being negative. We will talk a whole lot more about this later on. All right? So today's screencast was strictly about higher order derivatives. And I should say, I've been using that phrase, higher order derivatives. The order of a derivative is just the number of times you take the derivative, right? So we've dealt with first order derivatives and what the first order derivative means. Now we're looking generally at higher order derivatives, but very, very specifically at the significance of the second order derivative, okay? There is homework that accompanies this screencast. Let me go get it for you. Okay, here is homework pertinent or relevant to this higher order derivative, and 73 is such a fantastic question. I love it. Love, love, love it. All right, goodbye.